Good morning, esteemed colleagues and friends of the University of Illinois, Chicago, colleagues and friends of the University of Illinois, Urbana-Champaign, and colleagues and friends of the University of Illinois, Springfield. Welcome. Buenos días, estimados colegas y amigos de la Universidad de Illinois. Bienvenidos. Bienvenidos investigadores de varias instituciones de México, también universidades de El Salvador, Centroamérica y otros países latinoamericanos que nos escuchan hoy. A special welcome to students and to distinguished authorities from different institutions. Thank you for your distinguished presence. We appreciate your presence. My name is Elvira de Mejía, the director of the University of Illinois System Initiative, I-MMAS, Illinois Mexican and Mexican American Student Initiative. Welcome to the second symposium on energy that the University of Illinois Mexican and Mexican American Student Initiative organizes. I'm humble and thankful to facilitate this important and urgent initiative. I thank the president of the University of Illinois, Dr. Timothy Kalin, for his leadership and enthusiasm, recognizing the need and the opportunities that I-MMAS presents. I-MMAS represents a culture of support, building pipelines for Mexican and Mexican-American students, smoothing the path and retaining as many talented students as possible. With our peers in Mexico, I-MMAS will enhance ongoing efforts by the system's 3 universities to expand Mexican and Mexican-American educational opportunities. I-MMAS' vision is to promote a more extensive network of Mexican and Mexican-American scholars at the University of Illinois system, with synergistic opportunities for research, professional development, and student support, while fostering a more equitable workforce of well-educated professionals capable of succeeding in life and providing solutions to pressing challenges in Illinois, Mexico, and around the world. I feel proud to be part of this second I-MMAS Symposium on Energy, with the participation of distinguished researchers from the University of Illinois and distinguished researchers from UNAM, Mexico, the National University of Mexico, and the University Tecnológica de Querétaro, Universidad Tecnológica de Querétaro in Mexico. This symposium was organized by Dr. Leonardo Chamorro, Associate Professor at the University of Illinois Urbana-Champaign, and by Dr. Victor Castaño, researcher at the National University of Mexico. The symposium, Opportunities and Challenges in the 21st Century, will highlight cutting-edge research, including the impacts of renewable energy on September 14, today, and sustainability and climate change on September 15, tomorrow. I hope you join us for both sessions. The objective of this symposium is to enhance strategic synergies among researchers in Illinois and Mexico on renewable energy, sustainability, and climate change. We thank all authorities and representatives of different institutions for the presence and remarks. Now, it's my privilege to introduce the 20th president of the University of Illinois, Dr. Timothy L. Kalin. Dr. Kalin took office in May 2015 and has led a new wave of growth for the state's flagship university system. System-wide enrollment has grown to a record more than 93,000 students. A new presidential initiative is adding a new world-class faculty, and the system is leading to pioneering new education and innovation initiatives, the Discovery Partners Institute and the Illinois Innovation Network. Dr. Kalin has more than 3 decades of experience as a teacher, as a researcher and administrator in public higher education, and in top leadership positions with national scientific research agencies. Before coming to Illinois, he served as Vice Chancellor for Research at the State University of New York, and he also headed the nation's most comprehensive university-connected research foundation. Earlier, he served as head of geosciences at the National Science Foundation, which provides more than a quarter of federal research funding for U.S. universities. He also spent more than 20 years as a faculty member and administrator at the University of Michigan. Now, we will have some remarks from the president of the University of Illinois, President Timothy Kalin.
And welcome to you all. Bienvenidos. I am Tim Kalin, president of the University of Illinois System, and I am delighted that you are able to join us for this latest symposium conducted by I-MMAS. I'm grateful to all of our partners for their continued support of this important initiative and the passion that they bring to I-MMAS. Today in particular, I'm honored that the Universidad Autónoma de Nuevo León, Universidad Tecnológica de Querétaro, and Universidad Nacional Autónoma de México are all here with us. I'm also grateful and pleased that our own Prairie Research Institute is playing a major role in this event. I-MMAS was created as a bridge between the University of Illinois System and our colleagues and their brilliant students in Mexico, as a way to collaborate around important challenges and opportunities, to find answers and create opportunities. The interconnected subjects you're about to focus on over the next 2 days could not be more important to us all. Climate change is clearly among the major challenges of our times, one that we must meet and get right. Many of the tools we'll need to do that relate to sustainability and renewable energy. Simply put, we must find ways to provide food and water for a growing global population and to develop local, regional, and international economies that allow people around the world to thrive. And to do all of that in ways that we can sustain while providing solutions to the already dangerous problem of the changing climate. That is all daunting, I know. The good news is that brilliant, innovative minds have been at work on these issues for a long time. You'll hear from some in this symposium. And in the students with us here, I also know that the next generation of bright minds needed to take on these challenges is already being developed. Dado todo lo que está sucediendo en el mundo estos días, tenemos la responsabilidad especial de brindar soluciones a las comunidades de manera que inspiren a los jóvenes y formen una asociación cada vez más profunda para construir un futuro saludable para nuestras sociedades. So again, thank you all for joining us this week and welcome. Bienvenidos y muchas gracias.
Deputy Executive Director, Prairie Research Institute, University of Illinois, who is joining us with welcome remarks.
Good morning. My name is Rick Winkle. I'm Deputy Executive Director of the Prairie Research Institute at the University of Illinois. And it is my pleasure to be here today with you to hear about the important collaborations before us and to learn more about the innovative strides that you are all making in your respective fields. But first, I want to thank all of the extraordinary sponsors, speakers, and esteemed guests for their hard work and support. Without all of you, this symposium would not be possible. We are here at a critical moment when the need has never been higher to create a robust and sustainable energy economy. At PRI, our mission is to conduct transformative research that benefits the people, the economy, and the environment of Illinois and the world. That mission is demonstrated by our pioneering work in carbon sequestration, which led to nearly 1 million metric tons of CO2 being stored in the Illinois basin, and creating some of the world's richest data sets on geological characterization of the subsurface. We are working with local power generating companies like City Water, Light, and Power in Springfield, Illinois, to construct one of the world's largest carbon capture pilot systems that is leading in the net zero efforts to slow the effects of changing climate. PRI is leading in the carbon capture projects across 10 states in the US and is helping industries explore ways to utilize the captured CO2 to grow algae that are used for animal feed, to create biofuels, and to enhance cement production. We are leading in the charge to meet the need for renewable energy, such as geothermal, and exploring Illinois as a source of critical minerals to help accelerate the clean energy transition. We like to say at PRI, our research is not only happening in a laboratory, it is happening out in the world. Bridging discovery research with societal applications and impacts. And at PRI, we get it. We understand that partnerships across governments, industries, and universities worldwide are essential to drive innovation. Collaborations like this one will play a significant role in overcoming the unprecedented energy, sustainability, and climate challenges before us. We look forward to learning more from all of you in the upcoming presentations. Thank you.
Thank you very much. Thank you. Now we have some remarks from Dr. Guillermo Pulido, representing the Universidad Nacional Autónoma de México, UNAM, sede Chicago. We have some remarks from Dr. Pulido.
Ladies and gentlemen, good morning. With a great sense of purpose, I'd like to welcome you all to this academic symposium organized by the Illinois Mexican and Mexican American Student Initiative, focused on the pressing issue of our time: climate change, renewable energies, and sustainability. Thank you, Dr. Elvira de Mejia, for inviting me to share with the audience a few thoughts. As we gather here today, we stand at a critical juncture in human history, where the choices we make have the power to shape the future of our planet and the generations to come. The topic discussed over the course of this symposium are not mere subjects of scientific inquiry. They are urgent calls to action that demand our attention, collaboration, and innovation. Climate change, far-reaching impact are no longer theoretical scenarios, but the stark realities felt across the globe. From changing weather patterns to rising sea levels, from the biodiversity loss to extreme weather events. Just remember a few weeks back the incredible damage caused by the fires in Maui or the devastation of the Canadian forest. Yet, in the face of these challenges, there is a hope that springs from the transformative potential of renewable energies, which offer us a pathway to more sustainable and harmonious coexistence with the environment. The strides we made in harnessing solar, wind, and other renewable sources remind us that the human ingenuity knows no bounds. Sustainability in all its dimensions is the bedrock upon which we must build our strategies, policies, and technologies. It is about recognizing the delicate balance between our societal needs and the Earth's capacity to provide it. It involves remaining how we are consumed, produce, and interact with our surroundings to ensure a thriving planet for our present and future generations. I was very glad to learn recently from President Timothy Kailin during the Council meeting of Discovery Partner Institute that Chicago will be the host city in 2025 of the Conference on Sustainability, Research, and Innovation, which unites global leaders in research, governments, civil society, and business to meaningfully advance progress towards sustainability. This is an exceptional, inclusive, and inspiring global platform for co-creating state-of-the-art solutions and innovations, and building a coalition of the willing to achieve a sustainable transformation. As we embark on this intellectual journey together, let us open our minds to new ideas, engage in meaningful discussions, and foster collaborations that contribute to a real-world change. The presentations, dialogues, and exchanges that you will unfold in the coming 2 days hold the potential to spark breakthroughs and inspiring actions. As we immerse ourselves in the symposium, let us remember to each contribution, no matter how small, bring us closer to a more sustainability future. I encourage all of you to actively participate our collective efforts that can contribute to navigate the challenges of climate change and curb a greener, more equitable world. Thank you for your dedication to these vital issues, and I eagerly anticipate the impactful discussion that lies ahead. Together, let us be the catalyst for positive change and leave a lasting legacy of environmental responsibility. Thank you very, very much. Muchas gracias por su atención.
Thank you, Dr. Pulido. Thank you very much for your welcome remarks. Thank you. And now a little bit of a switch, Dr. Castaño. So, MC, Master in Science, José Carlos Arredondo Velázquez, Rector of the Universidad Tecnológica de Querétaro, México, was going to join us, but this morning, Dr. Víctor Castaño will present his message. So, Dr. Castaño, please.
Good morning. Thank you very much. And I'd like to present apologies on behalf of Mr. Carlos Arredondo. He had some personal issues at the last minute this morning, and he asked me to convey his regards. He's very thankful, and I'm going to read his message. Good morning, President Timothy Kellin, Director Richard Winkle, Dr. Guillermo Pulido, Dr. Elvira de Mejia, participants of this symposium, ladies and gentlemen. It is a privilege for me to have the opportunity to address this brief message to you. For the Technological University of Querétaro and for the state of Querétaro, renewable energies, climate change, and sustainability are not only topics of great relevance and concern, but tasks to which we dedicate our efforts every day through educational programs, public policies, investment attraction, and scientific research and technological development. We are convinced that the best bet to take advantage of these opportunities and face the challenges in the 21st century, the title of this important event, is through the training of more and better experts who strengthen these efforts. That is why tech, during my administration, has given enormous importance to relationships with leading institutions in the world, such as the University of Illinois System and the National Autonomous University of Mexico, with which we hope to consolidate our exchange program and training young people from Querétaro who are eager to participate in the global change that our planet needs, and events like today's open the door for this collaboration on strategic issues of importance to both countries, as well as to get to know each other better as neighboring cultures and business partners. I express to you my best wishes for this symposium to be a great success, and I reaffirm my personal and institutional commitment. I thank the organizers and all the participants for their commitment, and we hope to welcome you all soon in Querétaro. Thank you very much.
Thank you very much, Dr. Víctor Castaño, and thanks to Maestro en Ciencias José Carlos Arredondo Velázquez, Rector of the Universidad Tecnológica de Querétaro. Thank you very much. Thank you all for your kind words. I thank all the speakers. I hope this symposium will spark new collaborations, new discoveries, and then many problems will be solved. It's my pleasure to introduce Dr. Leonardo Chamorro, Associate Professor in the Department of Mechanical Science and Engineering, College of Engineering, University of Illinois, Urbana-Champaign. Dr. Chamorro is the organizer, and he will be moderating today's session of the symposium. Dr. Leo Chamorro is an outstanding scientist, an outstanding engineer, and we thank him for his leadership and extraordinary contributions to renewable energy. Please write your questions in the Q&A link, and we will make sure to request the speakers to answer your questions at the end of the symposium during the discussion session. The symposium will be recorded. Dr. Chamorro, please.
Okay, thank you very much, Elvira. Welcome, everyone. So let's start track 1, renewable energy. So just a reminder, we have 15 minutes. You can use as you want. So it's the presentation plus Q&A. And then please write down in the Q&A tab in the link. And then, so we will start now with Professor Jinhui Yan from the Department of Civil and Environmental Engineering here at the University of Illinois, Urbana-Champaign, that he will present some computational work. Jinhui?
Yeah, great. So let me start to share my screen. Can you see my screen now?
Yes.
Yes.
Okay, great. Good morning, everyone. Thank you very much for having me. It's my great pleasure to participate in this event. So in this short talk, I will present some of our development in computational fluid dynamics, CFD, and the fluid and structure interaction, FSI, for wind and hydro energy applications. I will show you the methodology very quickly and showcase some applications. So let me begin with some background. United States is very ambitious in terms of wind and hydro energy. So from the wind side, the Department of Energy released a report around 2013. It predicts that by 2030, 20% of the total US electricity generation will be provided by wind, and this percentage will be increased to 35% by 2050. From the water side, we are also very promising. So here I extracted some statistics from the DOE report. So also the length of the US coastline is more than 12,000 miles, and each year the average tide and wave energy is about 2,100 terawatt hours. And if we only harness 20% of this amount with 50% of conversion efficiency, we would be able to generate 7% of the total US electricity consumption each year. And another attractive fact about wind and hydro energy is that if you look at the energy distribution and the population distribution in the United States, you would see that they are pretty much overlapped. So this means that renewable wind and renewable hydro energy can ride power where we need them, and we can significantly reduce energy waste during electricity transmission by developing those energies. So if you look at the evolution of the wind energy and the tidal energy technology development, you will see that the energy harvesting structures are becoming bigger and bigger and more complicated in terms of geometric design and material design. So for example, if you take a typical offshore wind turbine, and you will realize that involves very complex geometry and materials, and then the blade size, the blade diameter can easily reach up to 120 meters. This means that, the cost of each turbine will be very expensive, and the experimental tests are becoming more and more expensive if you want to study their performance and the energy generation efficiency. So as a result, high performance computing are becoming indispensable. However, this is very challenging. The first challenge is that the energy harvesting structures are very complicated. They have a very complex shape, they are big, and they have complex distribution of material properties. And the structural components are in relative motion, and this will give challenges for CFD and the FSI simulation. The second challenge is that those structures are subject to very complicated loading conditions. So here I use a offshore floating wind turbine as an example. So it's subject to gravity, and it's subject to high Reynolds number turbulent wind flows. It's also a subject to ocean waves, and then you have a very strong components of those loading conditions. So in order to address those challenges, I mean, my group has developed a fully coupled multi-phase computational fluid and structure interaction formulation, which couples aerodynamics, hydrodynamics, free surface, and the structure mechanics, I mean, to study the dynamic response and the energy generation of those complex turbines. So let me give you some details about this formulation. So first off, for fluid dynamics. So for fluid dynamics, we have developed finite element method formulation for multi-phase flow on moving domains. So this approach is based on upturn Lagrangian O'Neill approach. And in order to solve the multi-phase flow, we couple Navier-Stokes equation with Naval-Set method such that we can attract the water air-water interface. And then we use variational multi-scale formulation as a large eddy simulation model to handle the large Reynolds number turbulence. And for structural dynamics, we're using a new technology called isogeometric analysis. I mean, for some of you, you may know that in structural mechanics or solid mechanics, finite element method dominates this field. However, there is a huge gap between computer-aided design and the finite element method. So in computer-aided design, typically you use non-uniform rational B-splines to represent the geometry. However, in FEM, what you typically use is Lagrangian polynomials. As a result, in the industrial structural design loop through analysis, a lot of time actually are spent on how to convert the CAD model into a FEM mesh that can be handled by finite elements. And for the very complex structures like wind turbines, this conversion process can take very long, typically accounts more than 80% of the total design loop through analysis. So in isogeometric analysis, we feel that we can integrate design analysis. So we employ the same function that used to describe the geometry of the turbine and directly use them in the structural analysis. So this is an example showing you how we use isogeometric analysis to do a design, structural analysis, and the visualization. And during the process, no mesh generation is needed. We directly use the non-uniform B-spline in the representation for design analysis and the visualization. And we coupled isogeometric analysis for structural mechanics and the multi-phase CFD in order to do fluid and structural interaction analysis. So here, let me show you what you can do with this computational fluid and structural interaction framework. So this is just several case, those are just several case studies. So first of all, you can use the framework to study the interference between turbines in a wind farm. So what you see here is a full-scale CFD simulation of two back-to-back wind turbines in atmosphere boundary inner flow, considering temperature stratification. You see that when a flow hits the upwind turbine, a lot of tip vortex are generated. When those turbulent wake travels and hits the downstream turbine, you see very different turbulent structure. So this interaction is also reflected by this plot. This plot shows you the averaged wind profile along height, before the upstream turbine and the range between two turbines. You see that right after hits the upstream turbine, the wind profile is immediately distorted, and with reduced kinetic energy, because a lot of energy has already been extracted by the upstream turbine. And this is also reflected in the aerodynamic torque on both turbines. You see that after the wind hit the upwind turbine, the downstream turbine experienced a 15% drop of aerodynamic torque, and this will need to significant reduced energy generation in the downstream. And we can also use, this framework to study hydro turbines. So the one important issue in tidal energy is the free surface effect, because typically you install the turbines in shallow waters in the rivers. Many experiments have indicated that free surface has a significant impact on the tidal turbine performance. However, a few people had studied this. So in 2016, we did the first study of tidal turbine, study of the free surface effect on tidal turbine performance. So in order to review the free surface effect, we did 3 simulations. The first simulation is a pure hydrodynamic simulation without considering free surface. And we performed 2 additional simulations with 2 different tip immersion depths. So here is the most important result, which shows you the time history of thrust coefficient and the power coefficient. There are several important points I want to make here. So the first one is that you can see that the free surface CFD calculation agree with the experimental measurement very well for both shallow immersion case and the deep immersion case. And the second point is that pure hydrodynamic simulation is not accurate. If you fully immerse the turbine, it means pure hydrodynamic simulation agree with free surface simulation. This is not surprising, because if you immerse the turbine very deep, the turbine barely feels the presence of free surface. However, for the shallow immersion case, you can clearly see the discrepancy between the 2 different approaches. And the third point I want to make is that the tidal turbine performance is better in the deep immersion case. You can see both the thrust coefficient and power coefficient are bigger. In addition to uniform inflow, you can put some waves. So this is a free surface simulation of this tidal turbine subject to airway wave inflow condition. And you can see the interaction between the turbine and the free surface flow. And you can see how the free surface deformed and how it interacts with the tip vortex due to the rotation of the tower. And this visualization got a prize from TechPlot in 2017. Because you have the waves, as a result, the thrust coefficient and the power coefficient will experience very strong fluctuations. However, if you average the coefficients in the fully developed stage, you still see that as you immerse the turbine deeper, the coefficients will increase. I mean, this indicates that for those uniform inflow and airway wave inflow conditions, free surface has a negative effect on the tidal turbine performance. This conclusion is not surprising. However, you have to quantify that. I mean, what if the turbine performance in terms of realistic wave conditions? So in order to investigate the free surface effect in those scenarios, you have to perform rigorous calculation. So before I end my presentation, I want to highlight one more application. So we already know that based on my previous calculation. Let me go back. We already know that for the uniform inflow for the deep immersion case, free surface doesn't have an effect on a single turbine configuration. And here we want to know for the deep immersion case, if we have a multiple turbine there, does the free surface still have an effect? So we performed a free surface simulation like this with 2 turbines sitting back to back. So you can see that, see the free surface deformation, and you also see how the free surface interacts with the tip vortex. So here is the result. In order to review the free surface effect, again, we compute the problem using both free surface simulation and the pure hydrodynamic simulation. And you see that for the water speed and between the upstream turbine and the downstream turbine, hydrodynamic simulation over predict the velocity, the flow magnitude. You can see here. and this will be reflected in the thrust and the energy power coefficient, and those two plots, right, shows you the time history of the thrust and the power coefficient. You see that for the upper strain turbine, a low free surface still doesn't have an effect. The result predicted by free surface CFD and the pure hydrodynamic CFD are almost the same. However, for the downstream turbine, because of the free surface and the tip vortex interaction, and the downstream turbine, for the downstream turbine, free surface start to have a significant effect, because the water speed predicted by the pure hydrodynamics is significantly bigger. As a result, the power coefficient and the thrust coefficient predicted by pure hydrodynamic simulation is also bigger than that of a free surface flow simulation. So with this, I will stop my presentation. Thank you very much for your presentation. I'm happy to take any questions from you. Thanks.
Okay, thank you very much, Jinhui. Great talk. We have only 1 minute for questions. If you have one, please write it down. We don't have much time.
Okay.
But Jinhui, one quick question.
Sure.
I see the CP reach almost the theoretical limit in the slide before. Is that because it's just transient, or?
You mean this one? This slide?
No, the previous one. The previous.
This one.
No, next one.
Next one. This one?
That one. Oh, no. Some of that. Yes, this one. You see, at time 0.7, you almost reached theoretical limit.
Right. This is only transient. This is a time history, right? So this is fluctuating, right?
So locally, you can have that.
Okay. Yeah, locally I have that because it's an airway wave, right? When you experience the peak, you will have a very a big torque, but we average by using the the mean of the wave, mean flow of the wave. So this across. Thanks.
Okay, perfect, excellent. Thank you, Jinhui.
Yeah, thank you for the invitation.
Okay, let's move to our second speaker. Is Professor Victor Castaño, research professor from the Mexican Academy of Engineering at UNAM. Victor.
Thank you. Good morning to all. It is a pleasure indeed to be here with all of you. And I would like to take this opportunity to talk about one big issue, as you shall see, that the people pay little attention to, which is saving energy. Of course, we will be listening today and tomorrow about several innovative ways to generate energy, to store energy, but I would like to draw your attention today about another big problem, which is saving energy. According to the EU Environmental Protection Agency, the energy sector is the largest emitter of greenhouse gases in the atmosphere, contributing to climate change. So energy, of course, is very important. We need to use energy in our houses, in our schools, in our enterprises, but we have to keep in mind that every time we use energy, we are contributing to greenhouse gases. What can we do? Of course, expand access to clean technologies, modernize infrastructure, ensure energy equity. But I would like to draw your attention to the first, most important area: save energy. We are a world in which energy is largely wasted, as you can see here. These are the main sources of energy for mankind: petroleum, natural gas, coal, different sorts of renewable energy, and nuclear power. And at the right-hand side, you see the different end users, including transportation, industry, residential, and commercial. But please take a look to the middle part. About 38% of all the energy we are able to generate, we will lose, either during transportation, during storage. We really need, if we are going to have a more efficient world in terms of energy, to keep an eye on how to save energy. And that starts in our house. These are the different sources of heat generation in a standard home. From the roofing, we acquire about 50% of all the heat that we suffer inside the house. All the appliances contribute 6%, but also every time we open a door or a window, we are exchanging heat with the exterior. We also have through the walls some infiltration, and also we people inside the house contribute to the generation of heat inside the house. That means that we need to spend a lot of effort and money and resources in air conditioning. This shows that there is a very big increase in electricity demand for air conditioning. Keeping fresh a house, a school, an office is mandatory in many places around the world, either to keep it cool or keep it warm, depending on the season of the year. People have developed technologies to insulate the house against the exchange of heat. And normally what they do is to use thermal insulators, namely different foams, like the ones you are looking at here, which prevent the exchange of heat. The problem is that this is very costly, not only in terms of the price of the material, which is not expensive, but the labor involved in insulating houses and buildings. And also in terms of all the waste that is generated, because this insulator lasts only a few years. What we have done is to develop a paint, which we call nano-thermal insulator. Here is being installed in the roof of a big hotel in Cancun. And as a result, they reduce their energy consumption for air conditioning 25% within 2 months. This is a table that shows the thermal conductivity of different materials: steel, wood, acrylic, paraffin, polyurethane, which is the normal use, and our thermal insulator. And you can see that our thermal insulator is 2 orders of magnitude smaller in terms of thermal conductivity, which means that instead of using several inches thick of insulating material, we only need about 20 to 30 mils of an inch to be able to effectively insulate. We have already patents in the United States and in Mexico. And we have a program with a federal agency called FIPA-TERM, which is a fund for insulating thermally houses all over Mexico. They operate in the hottest areas, the warmest areas of the country, in the northern part near the border with the United States, and in the southern part, which are areas which right now can reach up to 40 degrees Celsius every day. By doing this, we have applied to the roofs and to the walls, and you can see here in this thermal image on the left-hand side, the amount of heat present in the wall without our paint, without our thermal insulator. And on the right-hand side, you can see the obvious difference. Our studies showed that in all those areas all over Mexico, we are able to reduce an average of 28% of electricity consumption in the world. In the last 10 years, this has been applied to 120,000 houses, which means a saving of 3,000 gigawatts, equivalent to 1.5 billion tons of CO2, equivalent to 75,000 cubic meters of oil, and almost 5 million of oil barrels saved by just simply insulating these houses. The other thing that I like to tell you about is that, as you know, the solar energy market is one of the fastest growing in the world, as you can see here, in different regions: Europe, North America, China, the Middle East, and so on and so forth. That's very good news. That's great that mankind is paying attention to the saving of energy. But the problem is that we live in a dusty world. This is a map that shows the amount of dust all over the world, and with the exception of the Arctic area and the Antarctica, the rest of the world is heavily covered with dust. This means that once you install a solar cell, within few months, they get covered with dirt, and the efficiency decreases very dramatically. This is a review on how solar panels lost power due to soiling. And this could be up to 50% in less than a year. So this is a very big problem. And you could say, okay, we can just clean it. But in some areas in Mexico, they have found that it's cheaper to put up new solar panels than cleaning them. In order to solve this, what we did is to develop nanotechnology coating, which is self-cleaning. I'm going to show you, as an example, a concrete wall, a standard concrete wall. Half of the wall is coated with this very thin coating. You cannot notice which part of the wall is coated until we use water. You see? This is not coated, and this other half is coated. It's extremely efficient against anything that contains water or oil. We already have US and Mexican patents on this. We are using this in different solar parks in Mexico. And this is an example of our results. Part of these solar panels were coated with our nano coating, and the other part was not. It is obvious the difference. And what we have found is that the loss after 1 year of exposure is less than 1% as compared to 50%. This is my data. we will be very, very interested in collaborating in this area with the University of Illinois system, not only for this particular application, but this coatings and this technology, we believe could have many other applications for energy saving and helping to preserve our planet. Thank you very much.
Okay, thank you very much, Victor. Questions? We have a couple of minutes. So, Victor, one question that I have immediately. So you have your coating over the PV cell there. And then when you have a dust, let's say the PV cell, if there is no wind, if there is no wind and you have the PV cell horizontal with your coating, a particle sediment can settle there, and then even if it is perfect, whatever, no friction there, no roughness, it will still block. So what are the minimum conditions to remove the sediment? Let's say incline, there's some wind.
Yes, normally all the solar panels are tilted, not only to prevent this soiling, but also to make more efficient the collection of sunlight all the day long. So what we are testing this in 3 very big solar parks in Mexico, and we found, as I said, that it is not perfect, but instead of 50% power loss, we have only 1%.
Wow.
Of course, what we are trying to do now is to combine this with some artificial intelligence and drone technology to make more efficient. The drone will be with the help of artificial intelligence in connection with the solar panels, supervising and blowing some wind or some air stream on top of the soil panels to prevent them from staying there, as you mentioned.
Perfect. But in general sense, the slope of this solar panel are more than the critical for the dust to settle down, right? Yes, I imagine.
That's correct. That's
Okay.
correct.
Perfect. Pretty exciting. Okay.
Thank you.
Perfect. Okay, so next speaker is myself. So I will.
Yeah, I will be sharing your talk. So I will be keep pushing you to keep on time. Please go ahead.
Okay. Okay. Thank you. Okay, so I will talk about the turbulence-driven power fluctuations on wind turbines and wind farm. A follow-up talk from what I did in the last symposium, but this time I wanted to stress to provide some points discussion on the measurements challenge. So when we measure, when we assess the performance of wind turbines, wind farm, they are very, very associated to the flow and flow fluctuations. And we have to measure, we have to model those flow fluctuations. And then there are many, many challenges to do that, at least in the measurement standpoint. As Jinhui mentioned, we are having larger and larger turbines, and measurements become more challenging. So first, a few words of my group. So we are an experimental group that use state-of-the-art flow diagnostic tools and theory to address many problems in fluid mechanics turbulence from a fundamental and apply areas in well turbulence, flow structure interaction, particle dynamics, and renewable energy. And we use Eulerian and Lagrangian approaches. So in general, as Jinhui pointed out, we are having larger and larger wind turbines and wind farms. There are many, many new challenges from scientific and engineering disciplines. So trends point towards building, setting those units in complex terrains, harsh environment, offshore environment with fixed and floating units. So we need to understand what is the role of the atmospheric boundary layer within the wind farms at different scales, the flow structure interaction, particularly in floating offshore units, meteorological effects, the wave dynamics, turbine-turbine communications, and then the aerodynamic loads, especially for those monsters that are 5 to 10 megawatts now in the larger, very huge wind turbines. 1 second. Okay. So the common approaches from the measurement standpoint, we have laboratory experiments and field campaigns. In laboratory experiments, we have many advantages, which is we have control setups, repeatability, cost usually is an advantage. We can get scientific value. We can do optimization. We can couple different effects, topography, flow, turbines interaction. But there are many disadvantages as well in laboratory experiments, which are, we have to ask, are the model representation of the system representative of to field scale? So we have scaling issues. So we have limited aerodynamic loads there, and cost is an advantage, but could also be a disadvantage. And usually the blade scale aerodynamics is pretty limited. The Reynolds number is much lower than what we see in full scale settings. So those are examples of laboratory experiments. In field campaigns, on the other hand, we have several advantages. We have the full scale, we have the real setups there, we have the complex real multi-scale turbulence across all possible scales. We don't have scaling issues. We can get directly scientific value. We can couple topography, all those natural effects. We can assess other phenomena, including thermal stability, diurnal and seasonal cycles. However, the disadvantages are they are very costly. Usually, is hard to analyze because we have huge flow variability, velocity variability in direction and magnitude. We have issues with parameter sensitivity. We have usually restricted spatiotemporal data and access as well. So what are the common techniques that we use to get measurements of the mean flow and fluctuations with described turbulence, which are critical for characterizing power and power fluctuations of wind turbines and wind farms. So at laboratory scale, we have single point sensors, which could be anemometers, pitot tube, hot wire, Doppler-based units. We have at laboratory scale a planar measurements, which typically a PIV or even volumetric representation with PIV, particle image velocimetry. And we also have a complementary advanced techniques, which is three-dimensional particle tracking velocimetry. All those techniques we can use it at laboratory scale. In the field, however, we have complementary tools. Most common are the anemometers, single points, cap propeller type sonic anemometer. We have solar LiDAR in different variation, vertical profile scanning, dual and triple scanning. We have satellite base measurements, scatterometer, and we can do particle image velocimetry at super large scale. But we need to see the flow. That is pretty challenging, but conceptually is possible. So we have consideration between this laboratory and field scale. We have to account, we have to evaluate, we have to assess, we have to question about what are the temporal and spatial resolution that we need to achieve for a particular project or development, accuracy and range. So let's see a little bit. So at the field scale, what we wanted, what we need is get mean flow, mean velocity. We wanted to get higher order statistics, let's say second order statistic, to assess flow variability, the variance. And then hopefully we would like to know how scale interact at different scale to scale interaction. So we would like to assess, to capture the turbulence dynamics, the turbulence structure, the structure of the turbulence. So what we have? So can we measure mean flow? Yes, anemometer can measure that. But can we measure turbulence? Well, a review paper already over 10 years ago, but is progressing slowly. A gold standard technique is LiDAR. Can LiDAR measure turbulence? Up to some extent. It is challenging to get very accurate data. And can we use other techniques? Yes, we can use other techniques, and recent studies show that we are approaching to estimate just the second order statistic in a reasonable way. And then, so in general, for field scale, we can measure mean flow. We are doing substantial progress in getting high order statistics towards measuring the velocity fluctuations. But in describing the turbulence structure, we need more research and development. Still is a question mark at field scale. On the other hand, at laboratory scale, we can measure mean flow. We can measure high order statistics, and we also can measure the turbulent structure. However, we are bounded by the scaling in laboratory settings. We are bounded by that. So let's discuss a little bit about this scaling issue at laboratory scale. So we several years ago, we show that at laboratory scale, the representation of wind turbine aerodynamics, wakes, not the wind turbine blade, but the wakes of the wind turbines and turbine-turbine interaction become Reynolds independent at values that are representative, are possible at laboratory settings. So we have that without problem. We can do that. It's representative. And also a study by Wong et al. Relatively recently, that they show that the characteristic of the wake at the scale turbines, comparing with those at full scale, are very, very similar. So having Reynolds number independence and very similar representation of wakes in the lab and the field, we can at least assess bulk behavior of turbine-turbine interaction in the wake, communication through the wake at laboratory settings. And then we can ask, of course, there are many other settings, like what happens with the aerodynamics, what happens with the power fluctuation at the small unit, what happens with if we wanted to use advanced controls on the units, what happens with the scaling at small scale. So here I present some of then you will have these slides. So here are relevant parameter scaling quantities at laboratory and field scales, so that we can transition between one and to the other, and we can assess different questions, different phenomena through this scaling. And then one more important thing, we introduced that if we wanted to study wind energy at laboratory setting, namely wind tunnels, we need to add another scaling, which is how the boundary layer scale with the size of the wind turbine. And then we recommend that the integral scale of the turbulence, the boundary layer, is on the order of at least 2 times the rotor diameter. That is representative of field scale units. I consider that is a very important quantity to account when you deal with we wanted to represent the field scale units. So in general, what are the measurement challenge to assess wind energy? The problem is we have a different scale, we have challenge. We have first at small scale, we have to characterize unsteady loading, power and thrust fluctuations, which are heavily dependent on the turbulence and blade interaction, or turbulence rotor interaction. Those are at small scale, particularly characterizing that very relevant. Then at larger scale, we have to account for turbine-turbine interaction to understand, to quantify, to model, to reduce unsteady loading and allow advanced controls. And also we have when you have wind farms, we need to understand this inner-outer flow interaction to replenish turbulent energy within the wind farm. And also, of course, to do to control the turbine wakes. And then at a very large scale, at meteorological scale, we need measurements as well, because we wanted to assess what are the local effect in the sense in terms of topographic, sea effects, local weather effects, air-sea interaction. Those kind of meteorological effects are also critical for assessing the design, optimization of wind turbines and wind farms. So we have extremely large multiple challenge across scales. So our flow diagnostic tools has to go through all those scales to assess. So this is a summary from the previous symposium. We have a model for single turbines. We have a model for wind farms that we can use and complement with measurements and then evaluate these models. And then what we have recently done, explore offshore topography and turbine-turbine interaction. Thank you.
Thank you very much, Leonardo. And now the chair is back to you. Thank you. We have no time for questions now.
Perfect. Thank you, Victor. Appreciate it. Okay. Our next speaker is Professor Bernardo Figueroa, a research professor from the Institute of Engineering from UNAM.
Well, thank you. Thank you very much for the invitation to this prestigious symposium. I feel very honored. Let's start. Do you see my presentation?
Yes.
Yes.
Yes. Okay. Okay. Well, I shut down the video just in case we have problems with the internet, so we'll have more bandwidth. And oops, sorry about that. So this talk will be about energy harvesting with oscillating foils, energy from currents. Those could be sea currents or rivers or any fluid flowing This work was mainly carried out by my colleagues, Professor Carlos Malaga from UNAM, and my former student, David Balam. The idea is rather simple. The principle is very similar to this experiment I showed you in this slide. When a kid sticks his hand out of the window of a moving car, he feels the flow of air, and depending on the angle, on the angle of attack of his hand with respect to the motion of the air, he will feel a force. This force will depend on the orientation of his hand, so he will be able to extract energy from the flow. That's the principle. Of course, you shouldn't allow your kids to do that. It's dangerous, but it was just for the explanation. So using this principle, we can think of devices maybe inspired in nature that can extract energy from a fluid, from a current. There are passive devices that transform the oscillating motion into rotary motion using mechanisms like this one I'm showing here. There are others that use, for example, a single airfoil like this one, which is rather big, as you can see from the picture. These are examples of research works. At the top, we see numerical studies. At the bottom, we see experimental studies. And as we can see in the last column, the efficiencies they were able to obtain are rather large. I have to say that most of these efficiencies, in the case of experimental and also in numerical, are obtained with tandem configurations, which means that there are more than one airfoil. And there are two notes I want to tell you about here. One is that most of the numerical studies are done with prescribed kinematics. Prescribed kinematics means that we move the airfoil in the simulation the way we want. Most of the people uses a sinusoidal trajectory, both in heaving and rotational motion of the airfoil. And then they calculate the efficiency with the forces and the velocity. But one has to be very cautious with those kinds of simulations, because we may obtain a very large efficiency, but maybe that motion, that particular Reynolds number and Strouhal number may not be realizable, because the motion of an airfoil is governed by the Newton's second law of motion, and this thing has to accelerate to a given velocity, and with the energy that possesses the flow, the current, it may not be possible to reach that particular combination with a high efficiency. So one has to be cautious with these large efficiencies. Another thing I wanted to say, one has to be cautious also with the high efficiencies we see with the experimental works we see in the literature, because most of them are obtained with velocities that are way higher than what we can see in the ocean currents, for example, which are typically a lot less than 1 meter per second. So in general, one has to be very careful with these things. The efficiency I will show you later will be very low, as we can see here from the last row of the first table. So don't be disappointed. It's just that I'm trying to be realistic here. Okay, so let's continue. The problem we are studying here is an oscillating airfoil. Here we see the airfoil with a chord C. I don't know if you can see my mouse pointer. Can you see it?
Yes, yes.
Okay, okay. This airfoil is moving just in the y direction. It's heaving up and down, and is facing a flow, a current, which has a velocity u infinite, far from the airfoil, and it's facing the flow with an angle of attack theta. This angle of attack will produce a lift force that will drive the airfoil up and down. And we will be able to extract energy with a generator, which can be modeled, well, in the simplest way to model it is through a damper. The angle of attack can be changed using an actuator, a torque applied at the center of rotation of the airfoil, maybe through a motor or some actuator. And this scheme is supervised with some measurement. For example, we can measure the angle theta and the velocity, and this supervising system will tell us if we are doing the extraction correctly, and if we are not doing it correctly, then we can correct the motion by actuating through the torque. So this is a closed loop controlled system. Here, the airfoil will be moving according to the Newton's second law of motion. So we are considering here the fluid structure interaction. Now, the first approximation of this idea of getting the most of this system would be to think of a very simplistic, oversimplistic view of the lift coefficient, which will grow as the angle of attack grows. As we can see from this sketch I put here, there will be a moment where if the angle of attack is too high, the lift coefficient will get to a maximum. This is stall in aerodynamics. In fact, when an airplane stalls, the airplane falls down. It's very dangerous. But here it's not that dangerous, so we can think of this particular part of the plot. If we stay close to the maximum lift, we will be close to the maximum energy harvesting. We have to take into account that this thing is moving up and down, and the relative angle with respect to the flow will vary, but that calculation can be done very easily, so that's not a problem. So the second law, Newton's second law of motion will give us the equations that model this interaction. Here we can see that mass times the acceleration equals the summation of forces. Same thing with the torques and the motion, the angular motion, where instead of mass, we have the moment of inertia. These integrals represent the hydrodynamic forces, the forces integrated over the surface of the airfoil, or the torques. And this T here is the actuator. We act on the system through the torque on the moment, on the center of mass of the airfoil. This torque will be proportional to an error. This error is the reference angle minus the measured angle. We give it a reference angle, which in principle will be close to the maximum lift, and that's the way we will have this closed loop control of the system, which I represent here as a block diagram. Okay, so how did we do it? We carried out 2D simulations using an open source code called OpenFOAM, which allowed us to modify the code and carry out the closed loop controller, which was a proportional controller, the simplest controller we could think of as a first approximation. OpenFOAM can have deformable meshes, and this characteristic allowed us to move the airfoil the way we wanted, up and down, and modify the angle of the airfoil. Note that the resolution of the mesh must be very fine near the surface of the airfoil. So important variables, there are many important variables here: the fluid characteristics, rho, mu, viscosity, the density, the mass of the airfoil, the moment of inertia, and that results in 8 dimensionless variables. So this is a very complex problem. Some of these dimensionless numbers, the efficiency, the Reynolds numbers, a dimensionless heaving where h0 is, let's say, the maximum distance we go up or down, the range, in inertia, an inertia number, a rotational inertia number.
One minute, Bernardo.
Oh la la. Damping radio, and this number which represents the gain of the controller. So this is a typical result. Here we see at the bottom the position of the airfoil represented by these figures. We have the power in the middle, and on the top we have the angle. The dashed line is the reference angle, and the continuous line follows the reference angle thanks to the controller action. And we can see that this is a cycle. At the beginning, this goes downwards, and we can see some power extraction. And when we have to turn around the airfoil because we reach the limit down to -1 of the position, we have to act on the airfoil. And we see with the dotted lines that we put some energy in order to turn around the angle of attack, and then we can continue extracting energy with the airfoil moving upwards, and so on. And we have a cyclic motion, so we can extract energy. So we can calculate the efficiency, which in this case, we plotted the efficiency against another dimensionless numbers that represents the force of the generator divided by the force of the actuator, which is represented by the gain K. So if the generator is too stiff, this torque would be very high, and maybe it could move very slowly, so that could affect the efficiency, and vice versa. So there's a commitment here we have to make. We did many tests with different dimensionless heaving ranges, and we obtained efficiencies of the order of 10%. For example, here we see a maximum. We plot the efficiency in terms of these new dimensionless variables. So the lessons we learn are, well, there are many lessons. I consider other configurations than improvements like a passive turnaround of the foil at the end of the range. That would save a lot of energy. Control energy can be large in those parts of the cycle. The forming mesh has many limits, and the most important thing is that the lift coefficient and torque coefficient are very complex.
Time.
Oops, sorry.
So let's wrap up. Let's wrap up now.
Yes, I wrap up very quickly. So the lift coefficient and the torque coefficient have to be estimated, very well estimated, in order to have a good control law. In fact, they show hysteresis cycles. They are very non-linear. So our efforts are now on this part, estimating correctly these coefficients in order to propose better closed loop control laws and obtain better efficiencies and optimize here. I wrap up here, and I'll leave you with this. Thank you very much.
Okay, thank you. We don't have time for questions, so we are going to move to the next speaker. Is Professor Eduardo Ramos from the Renewable Energy Institute at UNAM. Eduardo?
Thank you very much, Leonardo. And let me try to share my screen. Okay, well, let me try to see whether I can stick to the time allotted. And I will start with thanking the organizers and particularly to Leo, because I think this is a great opportunity to start collaboration with University of Illinois. Well, as you can see in the title, the title is a question: is it feasible to efficiently collect energy from hurricanes? This was just an idea to have fun. I started talking about this with Diego Canul, who's our student, and I think it has developed in a very interesting way. So let me try to give you a very brief introduction. We have the motivation for this work was that hurricanes are numerous and very, very energetic. As you know, the hurricane is defined as a structure in the atmosphere where the maximum speeds are around 33 meters per second. And we have the Saffir-Simpson categories. And if you have the very big hurricanes can have up to 70 meters per second, 250 kilometers per hour. And by the way, perhaps you might be feeling the effects of the Lee hurricane right now in Illinois. Perhaps it's going to go tangential to the East Coast. So you can personally comment about the intensity of hurricanes. So hurricanes are a great source of energy, and the people have been thinking about how to get the energy from them, just extract energy in order to turn it into useful energy. And in some other parts of the world, in particular in Japan, there's a company that has developed a system to extract energy from hurricanes. And as usual in the media, you can have the spectacular comments on this. For instance, they say that hurricanes can let a single typhoon, they call it typhoons in Japan, give the energy for 15 years. That's a crazy and very inaccurate statement. Let's try to analyze a little bit from the scientific point of view. What are the real possibilities? What are the real conditions under which we can extract energy from hurricanes? Okay, well, first of all, what is a hurricane? Essentially, a hurricane is a consequence of the thermodynamic disequilibrium between the atmosphere and the ocean. And a typical scales of a hurricane is just let me see if I can. Yeah. A typical scale of a hurricane is about 1,000 kilometers across, and it has an azimuthal velocity, as we have seen, of about 60 meters per second, even though up to 80 meters per second have been recorded. Now, this is a big statement. Okay, this velocity this air velocity is huge, but if we take a closer look at a closer look to the structure of the hurricane, we will discover that this is not so simple. A hurricane, essentially, the structure of hurricane is an upward stream of air that goes up, all the way up to the stratosphere, and then it comes down, and it exchanges energy, taking heat energy from the ocean and releasing the energy up in the upper parts of the ocean. Now, the azimuthal energy, the energy from the azimuthal motion, is concentrated in a region that is very close to the upward going current, and it does indeed go to very high values, 40 meters per second, but it is concentrated in a region that is about 100 kilometers. So, of the whole of the structure, it has only a very limited region where the density of the energy is high. Let me just mention that if we consider the whole energy of the hurricane, okay, it would be very interesting because it is comparable to the energy powering in Mexico, power consumption. But again, let's look at the possibilities of efficiently collecting the energy of hurricanes on land. First of all, we're going to explore three possibilities. First of all, let's explore whether we can catch the energy in land. Well, first of all, if we want to catch the energy from a hurricane, assuming that we are on land, then one of the difficulties, I will list some of the difficulties, but let me talk about this a little bit in detail. One of the most important difficulties is that we don't really know where the hurricane is going to go. For instance, I remind you that we have that the trajectory of hurricane from the weather services is a trajectory that widens as it goes in future. So we don't really know where it is going to land. So if we wanted to catch the hurricane on land, then we would have to be running around using presumably roads or rail tracks to actually go to the place where the energy is. This is not the only difficulty. We have also the problem that we don't actually know what is the strength of the hurricane. And even if we are lucky enough to be in the right place in the right time, then we will have to solve the problem of energy storage, because the hurricane is very short-lived. It's about 16 hours. So we will have to be very careful in storing the energy very, very efficiently in storing energy. Okay, even though this will be very difficult, there will be many challenges. Nevertheless, as I commented before, there is the technology has been developed by a company, Shell Energy in Japan, and if you they claim that they have got that their device has been able to catch the energy of a typhoon, about 30 meters per second wind, but it's very expensive. If you want to try your luck, you're welcome to buy one of those for $250,000 US dollars. And also, as we said, you will have to be running around in to catch the energy. Now, what happens if, second idea, what happens if instead of being on land, we are on the sea, in particular in the Gulf of Mexico? This would be a very interesting idea because if we talk not only about hurricanes, but also all the tropical depressions that occur on sea, then we have a much more numerous possibilities. And just to give you an idea, I'm showing you the different trajectories here in the nearby region of the peninsula of Yucatan. Now, how do we catch the hurricane energy on land? What happens if we take a very robust wind turbine and put it on a boat, and as we said before, just to run around and try to catch the energy? Well, this is not such an outlandish idea. There's some companies that actually build structures that will be very similar to the ones that are needed based on Magnus effect, that build these systems on ships. So this would be interesting, and let's see whether we can actually fulfill the conditions. This is the Hurricane Delta going through the Yucatan Peninsula and running around in the Gulf of Mexico. Now, if we want to put it in a vessel, then we would have to travel at about 7.5 meters per second. Also, we will have to struggle with waves because the strong winds coincide with strong waves on the sea. So the vessel would be very, very strong. Now, we can use, instead of ships, vessels, we can try to use sea drones. And again, the technology has been developed. This an American company, Drone, that has gone through hurricanes and has extracted energy. Now, very many adaptations would need to be done because this technology was not developed to extract energy from hurricanes, but to capture information from hurricanes. But nevertheless, we are more or less
1 minute, Eduardo.
yes, we're not so far from getting the technology. Now, is it possible to, now that we are on sea, perhaps we can also try to get energy, not from the air, from the wind, but also from the currents that are generated by the hurricanes. This is an enormous source of energy, and what we're thinking of right now is that this would be the best way to go, to try to extract energy from the atmosphere and from the ocean in the passing of the hurricane. Also, thermal energy, which I haven't had the time to talk about, is available. Good. My conclusions are: let's try to answer this the question: is it possible or feasible to efficiently collect energy from hurricanes? The answer is perhaps, and our study indicates that we need a deeper understanding of the physics of the atmosphere and ocean, and also we have to design an unmanned collecting device to extract all manifestations of energy. And this is the end. I think I have only 10 seconds for questions and comments.
Okay, thank you very much, Eduardo. We don't have much time, so I encourage you, the attendees, to write Q&A. So at the end we can discuss about that. So, thank you, Eduardo. Again.
Thank you.
Our next speaker is Timothy Grudlow, a principal research scientist from the Grange College of Engineering, nuclear plasma and radiological engineering. Timothy?
All right. Yeah. Hi, everyone. Thanks for the opportunity to present here. I'm looking forward to talking about our project. And I'd like to echo what someone said before about this being an excellent opportunity to collaborate. I think there's a lot of really cool things going on that are very relevant. So I will share my screen. Please let me know if my slides do not show up.
We're good.
Excellent. Yeah, so I'm Tim Grunlow in NPRE at the University of Illinois. I am the Associate Director of the Illinois Microreactor Demonstration Project. And I'll give a high-level overview of the project that we're working on and some of the forward-looking objectives. So, nuclear energy is not always combined with renewables, but I think we have a real opportunity here to kind of merge renewables and nuclear to achieve some of the energy resilience and carbon freeness of future energy. So this picture that we have here, this is a mock-up of where we want to go. So we don't have a reactor on campus yet. We are in the process of licensing one. Of the buildings that we see on the screen, two of them currently exist. So this one that I'm drawing right here, this one is on campus already. It's currently being used to a low level. We're proposing to retrofit it to use for research. This building on the right is Abbott Power Plant, is a fossil fuel plant that provides the steam needs for the university as well as some electricity. The remainder here is our proposed building. This is a parking lot currently, but we're planning to build a microreactor. I'll explain a little bit more about what we mean by that. That will be underground and provide nuclear heat that will feed into a thermal energy storage system, which is very similar to what you would see in concentrated solar power, for example. This would be used to generate steam, which would go over to Abbott Power Plant. So, as I get into it, we'll talk about what microreactor is and how it's different from the current generation of nuclear. In the United States, at least, all commercial power plant is from large light water reactors. By large, we mean a gigawatt of electricity at least. Often there's several units on site, so we're looking at single sites that power millions of homes. And this was designed in an energy market of the 50s, 60s, and 70s. So things have certainly changed in the energy market. And then also after the 3 Mile Island event, there was a lot of requirements placed on these reactors that made them very expensive to build. They became very cheap to operate once you were able to amortize the capital cost. But the extreme production has prevented us from building many of these in recent years. Although I will say in just the past couple of weeks or months, some new designs did come on board in the US. So it's a very exciting time for nuclear. With the increased interest in carbon-free power and reliable power, nuclear is getting a second look. And then also, all of the new technology advances that have come up in other industries, since the 70s or 80s, which is what a lot of the current nuclear technology is, are going to be integrated into the new nuclear designs. And so this has let people rethink things. And to fight some of that construction costs that I mentioned earlier, we're looking at factory fabrication of as much as possible. And this is where the term microreactor sort of comes into existence. So if we go all the way to the small end, you can design a small reactor on the scale of a megawatt or something, and you can transport, this entire reactor on the back of a truck. You can drive it to where you need it, turn it on, and go. As you get a little bit bigger, it gets harder to do that. You move into the small modular reactors, which are tens of megawatts to hundreds of megawatts. These are often partially fabricated in a facility, and then some are built on site. You're seeing a lot of proposed vendors, or a lot of vendors proposing putting several of these on a site to basically match a very large installation. And then we do also have new designs that are of that gigawatt scale that have a lot more safety features. They use a lot more advanced construction techniques. So nuclear has the right size for what you need these days. It's much more flexible than it used to be. And so I'll say a word on safety, because that's one of the first things that people say when you hear about nuclear power. A lot of folks think of Chernobyl, 3 Mile Island, Fukushima. One thing that these have in common is what caused the accident was decay heat. So when you turn a nuclear reactor off, there's still some heat generated from the radioactive decay of fission products in the nuclear fuel. And this heat comes from this heat is on the order of a couple of percent of the operating power right after you turn off, and then it very quickly decays to well under 1%. And so if you're at a very large gigawatt electricity, which means 3,000 megawatts of thermal energy, even if you're at a percent of power, you're looking at quite a bit of power that you have to get rid of. And typically, Fukushima, for example, relied on large diesel generators to remove that. And those were damaged by the hurricane, and so you lose your active cooling. Now, if you go to microreactors, you go to, for example, 15 megawatts thermal, you have, 1/200th of the nominal power, which means you have 1/200th of the residual power. And so here you go from, quite significant cooling needs to something like, what a car engine generates, which is much more easily dissipated through passive means. And the good thing about passive means is the energy is dissipated through nature, not through engineering, not through, operator action. So it becomes impossible to disrupt that, except for extreme cases. Each design also has extra safety measures that make them even more safe, which I think is beyond the scope of this talk, but I'd be happy to talk about those any other time. And so, one question you might ask is, if we're gonna demonstrate a microreactor technology, why Illinois? So Illinois has demonstrated nuclear leadership from the beginning of the nuclear age. The first sustained fission reaction as part of the Manhattan Project happened in Illinois. Argonne National Laboratory became one of the chief nuclear laboratories in Illinois, which is by Chicago in the north of the state. And the first commercial nuclear power plant was also in Illinois. And today, most of our electricity is nuclear, and the vast majority of clean energy, and here by clean, I mean not carbon emitting energy, is nuclear. And further, we had a research reactor on campus for 38 years that was decommissioned in the 90s. So this was safe operation. We invited the public to come visit this reactor and see things, see how it works. And even today, we get people saying that they really appreciated being able to see that, and they're excited that we're proposing building another reactor on site. So we're planning on leveraging Illinois' leadership in nuclear, the University of Illinois' experience with nuclear. A lot of folks that were here for the trigger reactor are still involved. And so this gets to the Illinois microreactor demonstration project, which is what I work on every day. So we have, as part of our project to deploy a microreactor on campus, we have 2 core missions and a cross-cutting mission. So as a university, one of our chief missions is going to be education, training, and engagement. So, education is using this as a teaching aid. we want to train reactor operators, which as this will be a commercial unit, will be able to do that. We're also looking at very actively looking at cross-training. So in the future, if carbon reduction does continue with the momentum it has and even picks up momentum, we'll be looking at displacing coal, natural gas plants, which a lot of folks work there, a lot of very skilled people work there. And so we're looking at, how can we leverage that, keep those people employed, and also maintain that experience with as little retraining as possible. The other core mission is research and development. The paradigm of nuclear has to shift for us to be able to operate more flexibly in the more diverse grid of the future, and to realize some of the business plans that are proposed. And we will be in a unique position to perform that research and development. And finally, we have the cross-cutting mission, which is simply at-scale demonstration. So our unit will be a commercially representative unit, and by tying it into Abbott, we will demonstrate that a reactor can be sited in a location near existing infrastructure, that it can be tied into existing infrastructure. And this is an idea that's really important for commercializing the new nuclear concepts that has not been demonstrated in the United States at all, and it's only been demonstrated globally in a few instances. And so this demonstration will be a very important part to support industry. So I'll talk a little bit about the technology. So this is our reactor. It's designed by Ultrasafe Nuclear Corporation, headquartered in Seattle, Washington. It's a high temperature gas reactor, which means it is not water cooled. It is cooled by helium. It is powered, by uranium, and it's this underground design. So here is an animation that shows how it works. We have helium that goes through there's a blower up here that acts, as the circulator. It pushes helium down through the outside of this concentric pipe, goes around and enters the core from the top, where it picks up nuclear heat as it moves down, and then hot helium goes through this heat exchanger, which we see here, and it exchanges the heat to a molten salt, which goes up. And again, at this point, it's essentially equivalent to a concentrated solar power system. The geometry of the core can be shown over here, where it's basically solid blocks of graphite with small fuel elements embedded. And you go to smaller scales, and the point of this, without going into too much technical detail, is that as you're looking at the macroscopic core, you're looking at many barriers of protection that keep the radioactive material from entering the environment. So this has been designed on decades of experience on how to keep reactors as safe as possible. And as part of our forward-looking research, we're looking at things of how to operate these things more efficiently, how to use fewer operators without compromising safety, and how to exploit other addressable markets. And I pulled this particular example because of the context of this talk. But renewables are clearly a growing part of the energy portfolio everywhere. People are aggressively looking to expand it. I see new neighbors every day putting up solar panels, which I'm very excited to see. We have solar farms nearby, wind farms nearby. It's very exciting, and nuclear has an opportunity to be a part of this and provide some critical grid stability without increasing the carbon emissions. And we're looking at how we can design the operational paradigms to enable that. The storage is a critical piece of that. And the University of Illinois campus has a very diverse grid in terms of both energy users. So, we use a lot of steam, we use a lot of electricity, we have supercomputers. We also have a diverse energy generation portfolio. So we have Abbott, which is a fossil fuel. Okay, yeah, wrapping up here. We also have on-site solar farms, and we have a wind power purchase agreement. So we have a mix, and we have a lot of data on these, on all of these, the sources and demands that we are using to develop operational models. And so I'll wrap up there. And so, the thoughts that I'll leave you with is this is an exciting time in nuclear, that we see that there's a really unique opportunity to integrate with the grid of the future, which includes lots of renewables. And we think Illinois is in the right place to see this through. And so I'll stop there. And if we have time for questions, I'd be happy to take questions. Otherwise, thank you.
Okay, thank you very much, Timothy. Very nice presentation. Okay, so our next speaker is research professor Germán Buitrón from the Institute of Engineering at UNAM. Germán?
Yes, thank you. Can you hear me?
Yes, perfect.
I'd like to share my, but I can't. Thank you very much for this opportunity to allow me to present our work. I'm going to talk about a different topic that we have been here this morning, and is about obtaining renewable fuel from waste and wastewater. Next, please. So this is the work that I'm going to present from my PhD student, Eder Ordóñez, and it's about biohydrogen production using agroindustrial waste. Next, please. The problem, what I'm going to talk about is a particular problem, but it's in general applicable to any industrial wastewater. This is the case of the wastewater from coming from the fabrication of cheese. In particular, we are dealing with this so-called cheese whey. Cheese whey is the product that is obtained after the cheese is fabricated, and it's an effluent that poses several problems to when it's discharged without treatment. Next, please. So, which are the characteristics of this wastewater? Is it has a very high content of organic matter, acidity, and a high solids content. Next, please. And this difficults the treatment of the effluent. So we need a particular process, and we can use, for example, anaerobic digestion to obtain methane. Next, please. But there is a problem, in particular with the acidic cheese whey. When the cheese is fabricated, we have two types of cheese whey. The sweet cheese whey, that is at neutral pH, and this is valorized to produce food for animals. But the acidic cheese whey has a problem because when it is neutralized to put in an anaerobic reactor, it coagulates. So it's a very big problem because it cannot be treated directly, and some actions have to be taken. And for that, we implement. This is a call that was made from an industry and to produce or to treat the wastewater, of course. So we can implement two-stage processes. In the first stage, we obtain hydrogen or medium chain carboxylic acid, and this first transformation that we hydrolyze all the compounds that are present in the effluent are transformed in acid that can be very easily neutralized and put in the methanogenic reactor. But one additional issue is that in the first stage, we can obtain hydrogen. So in the first stage, we can obtain hydrogen and then methane. Of course, this hydrogen is not enough to run a car or a plant in a city. No, but we can use this hydrogen, combining with the methane, and improve the functioning of the machine that produces electricity, because it has been seen that the combination of hydrogen in certain amount, small amount, with methane make the production of electricity better, because the machine doesn't produce, for example, nitrogen oxides that are very strong gas, greenhouse gas. So, and after that, we have the treated water. Next, please. So, which is the problem here? Usually, when we obtain the cheese whey, we have lactate and lactose. Lactate is an acid that was fermented from lactose, that is a sugar. The problem is that when it is stored in a tank before the treatment, all the lactose sugar disappear and is transformed in lactate, the acidic form. And this is a problem, next please, because in the conventional route for hydrogen production, sugars are used. So the sugars are used and carboxylic acid are produced and hydrogen is produced. So how we can obtain hydrogen from an acidic effluent in which the sugars as lactose are transformed into lactate. Next, please. So this is the objective of this research of my PhD student, to evaluate alternative pathways using lactate and lactate acetate as substrate for hydrogen production using acidic cheese whey. Next, please. So for that, we use cheese whey from a factory of Querétaro, fermented acidic cheese whey. We obtain this effluent right after the cheese is fabricated. As in the literature, everybody assumes that is going to have in the practice, but it's not. And we use the fermented acidic cheese whey, that this is real effluent that we are going to obtain when we want to treat this type of wastewater. So we use these two, the theoretical so-called acidic cheese whey and the fermented acidic cheese whey, that is the real effluent that we are going to have in the practice. Next, please. How we do that? Well, we have to adapt an inoculum also that it can be used in a practical way. So, and a granular activated sludge that is used in an aerobic reactor, this black one, granules of microorganisms, principally archaeous microorganisms, and we adapt into these hydrogen production microorganisms. And how do we do that? Well, after 2 weeks, maintaining the acidic pH and a very low hydraulic retention time, we wash out all the archaeas that are present here. We only use the skeleton of these granules to promote the growth of the hydrogen-producing microorganisms that are present there also in this original inoculum. Next, please. The goal here was to stop the methanogenic activity, of course. And we worked that in a lab-scale reactor with this parameter. It's an expanded granular sludge bed. Next, please. I'm not going to go further for the details, but I want to see that we run the reactor for about 3 months, and we studied several parameters. First was the first stage was the acclimation of the sludge, as previously explained you. So we use the cheese waste as it comes from the factory just after the fabrication of the cheese, and the fermented cheese waste in a 50-50 proportion. Next, please. So these are the results. In the first stage, as I told you, we studied the acclimation, but in the second to in the third to the sixth stage, we studied the influence of the hydraulic retention time. These two different hydraulic retention time, maintaining the pH constant. And as you can see here, the best was found at 4.5 hours. Next, please. The next experiment was to maintain constant the hydraulic retention time, and we varied the pH. And the best was here with a pH of 5. Next, in the last experiment, we add acetate. We maintain the best conditions of hydraulic retention time and pH, and we add acetate. And this is the hydrogen production rate in normal liters of hydrogen per liter of reactor per day as a function of the different days of operation of the reactor. So you can see here that there was a peak in the maximal production. We maximize the production of the process, but the relevance of this study is that we are not using sugar. Next, please. How we can explain that if we don't use sugar, we can obtain hydrogen with such a high productivity. So we made an analysis of the microbial community present in the reactor next, and we found out that there were 2 microorganisms, next please, that were present. And this is Lactobacillus and Clostridium.
1 minute.
In every case, these are the microorganisms that are really good for do that. Next, please. So these are the pathways that we found to be present in the reactor. The acrylate pathway, where lactate is used to produce hydrogen, and the pyruvate ferroxyl oxyreductase pathway, where acetate serves as electron acceptor. If you want more details, we have these 2 publications in Bioresource Technology and the International Journal of Hydrogen, and we explain with detail that. Next, please. So finally, the presence of lactate-producing bacteria, it has been told that are detrimental for hydrogen production. However, next, please. Some studies have support that we can see that it is enhanced when, next please, these 2 types of microorganisms are present, that is acidolactic bacteria and Clostridium bacteria. Next please. So in conclusion, it was demonstrated that hydrogen can be produced using lactate as substrate, and when we add acetate, this productivity can enhance by 3 times. And of course, the presence of Clostridium and Lactobacillus positively correlated with hydrogen production and lactate consumption. Next, please. I only like to thank the Consejo de Ciencia y Tecnología from the state of Querétaro who financed this research, and also all my research team at the Juriquilla campus of the National University of Mexico. Thank you.
Okay, thank you very much, Herman. Very interesting talk. We don't have time for questions. Please write it down in Q&A. We can revisit them after the symposium. Okay, so our next speaker is Professor Yuanhui Shang, founder professor from the Department of Agricultural and Biological Engineering at UIUC. Professor Shang.
Thank you, Professor Cameron, and thank you for LVS for inviting me to this project. Can you see my screen well?
Yes. Yes.
Okay. So I'm switching the gear a little bit again. This is about the biofuel, different from the other renewable energies like solar, wind, biogas, etc. This is a focus on the conversion of bio-waste into liquid fuel through hydrothermal liquefaction. In short, it's HTL. So I'm going to give a bit of a higher level overview of several projects together on this program. Is the theme on hydrothermal liquefaction and upgrading into jet fuels. That's the current effort. So based on the biogenic hypothesis, all fossil fuels found on Earth, petroleum, including oil shale and tar sand, natural gas and coal, are formed through process of so-called thermochemical conversion. Thermochemical conversion including hydrothermal liquefaction, pyrolysis, and gasification. My research is focused on the hydrothermal liquefaction. And those through these hydrothermal processes then formed the biofuels from the biomass through millions of years. In particular, oil is converted from algae, and coal from wood and peats, and natural gas from both, but at higher temperatures through gasification. So that is a kind of higher level of principle of this hydrothermal liquefaction. So by mimicking Mother Nature's millions of years process of turning deceased living matters buried underneath the ground into the petroleum, the food waste, algal bloom, and other bio wastes, including agricultural manures, etc., have been converted into the crude oil in past several decades of research. This conversion can be achieved in minutes using hydrothermal liquefaction in 10 to 40 minutes. So DOE has recognized the hydrothermal liquefaction as one of the major pathways. This only happened in past 10 years, but it's really get a lift since 2017, but 6 years ago, as HTL recognized as the major pathway for the biofuels. And more recently, FAA and DOE set the target by 2050, all our jet fuels is going to become from the biofuel, renewable fuel. We are going to really replacing the fossil fuels by 2050. So only 27 years away. So now what's at stakes? The problem is now we want to focus on recover and reuse the food and agricultural waste. It is challenging, but it's also promising. This is especially important in terms of sustainability and the circular bioeconomy. And in US alone, that we estimated to have 16.3 million tons of food waste alone. And that's representing $161 billion loss. And also we have 77 million tons of the collectible bio waste annually from the food systems. Those are from the DOE and USDA's annual report. Those biomass is generally considered expensive burdens, such as the collection and dumping phase. On the other hand, it is high in nutrient, high in carbon and energy that can be recovered and made into the valuable byproduct, such as transportation fuels and biobinders or other biochemicals. So our research hypothesis or objectives is the waste biomass derived from those bio waste stream can be converted via the hydrothermal liquefaction into high-value bioproduct, including transportation fuels, biobinders, and the nutrients can be recovered for the reuse of agricultural production, and thus to achieve the circular bioeconomy. So I'm going to use this example. So this is the ongoing research for, I have a 2 DOE project to dealing with the food waste and municipality wastewater sludge. So in this one, we target on 2 types of food waste. One on top is from a kind of a sort of a restaurant waste. And the second is from the food processing plant. First, they are homogenized, and then we do all this biochemical analysis, including proximate analysis, here, right hand, and elemental analysis. After analysis, we doing an array of the lab tests to determine what the hydrothermal liquefaction conditions. This including the temperatures, retention time, and the solid content, etc., to determine the best or optimum operating conditions following the severity factors. The severity factor is really a function of the reaction temperatures and retention time, and then to see what's the best conditions we can get the crude oil fraction. So through those study, then we determine the operating conditions for our pilot reaction. Again, this is the high overview. My lab has been conducting this research over 27 years, past 27 years. We gone through all the batch reactors, several generations for continuous reactors. And now this is the pilot reactor in my lab. It has the process capability of 1.5 ton per day of bio waste. It's on the trailer. Actually, in the Army project, we've been hauling to the field last year to Florida and this year to Texas to treating the algal blooms. And you can see this through this reactor. At the end, the product is the biocrude oil. So this is the at the end of here, and this is the oil skimmer. And this is in particular, this one is from the food waste. Okay, so we get to the food waste. These are some samples. So here is the different bucket, are the crude oils at the end we collected from the reactor. And at the end, here is the post HTL aqueous, or we also call it post hydrothermal wastewater, PHW. So those are both are valuable. Oil stream can be further upgraded into different transportation fuels, in particular diesel and jet fuel. And heavy fractions could be biobinders for road pavement. At the bottom is the aqueous, still contain most of the nutrient, the nitrogens, phosphorus, whatever in the original waste stream, we can recover that for recycling for new agricultural production again. And then for the crude oil part, we are doing an array of the pre-treatment, okay, to upgrade for the transportation fuel. Here, I just show you a couple of results. This is from the food waste. Through the TGA analysis, and we can get different fractions, including diesel, those purple range, and the gasoline, and kerosene, which is the jet fuel range. Then our job is to take those light fractions, including the jet fuel and the diesel fuel range. We want to upgrade it into the jet fuel. Here is our goal, and the current my current project is focused on doing all this upgrading using different catalysts, and we are also developing our own nano size catalyst in collaboration with the chemical engineering and civil environmental engineering. And the major process including the denitrogenation and the hydrogenation and the deoxygenation, the hydrogenation. Our goal is this big black blocks is our crude oil produced from the food waste. Then we are focused on to this different upgrading processes to obtain at the end. This is our goal, is the jet fuel. This is the DOE and also the US DODs, they all want to get the jet fuels through the food waste, and that's what we are aimed at. So just to give you a kind of overview of the project. So this right now my group have this reactor we developed in collaboration with the industry and sitting on my lab. So this allows me to produce enough amounts of the crude oils and the wastewaters for the downstream research, including upgrading and including the nutrient recovery. And you can see from the inside, outside the view, this is last year's picture we're holding. This is in the Army project to dealing with the algal blooms. So this reactor, again, that has a capability for treating 1 ton per day. So we can obtain enough of the crude oils for upgrading work. This project, and this is funded by the USDA, And particularly, we are focused on the food waste and swine manure. The goal is to end product is focused on the S folders. So we through this process, we treat the bio waste, including food waste and swine manure, to get light fractions for diesel and jet fuel, and the heavy fractions for road pavement. And the wastewater we aimed at to grow vegetables, lettuce. So this is a part of the circular bioeconomy. In parallel, working with Princeton University and the national labs, is focused on the food waste for jet fuels. So my team is primarily responsible for converting into the bio-crude oil and then upgraded into the jet fuel. The other partners are dealing with the wastewater and some of the hydrogen production from the wastewater. So that's those are projects in parallel, and we also now dealing with municipality wastewater slugs. And then again, the approach is it takes the wastewater, convert it into the crude oil, and then upgrade those crude oil generated from wastewater sludge into jet fuel and marine fuels. So that is ongoing. Again, this is still in the research and the development stage, but this is in the past 5 years, this becomes a really emerging hot topic, because we are aimed at replacing the traditional fossil fuel based jet fuel. And our goal is by 2050 that we can replace our jet fuels with a renewable fuel. So with that, I will entertain some questions. Again, this is a high level of overview without much of the technical details, but just overview of this several projects. Thank you.
Okay, thank you very much, Professor Chang. Very interesting, several research there. Okay, we don't have time for answering your questions, so please leave the message there in the Q&A. Okay, we will, thank you again, Professor Chang. We will move to Alejandro Castañeda, a research professor at Renewable Energy Engineering at Universidad Tecnológica de Querétaro. Okay, Alejandro.
Yes, hello. Alejandro got the flu today, so he's in no condition to present. So he asked me to present his work, and I will take the opportunity to also share with you a possibility for collaboration, which is the following. Alejandro is an electronics engineer. He's one of the, I will say, leading experts in Mexico in advanced electronics, in particular, embedded microsystems. He also is an expert in artificial intelligence, Internet of Things, and he and I have collaborated for many, many years doing both research and technology. We are currently producing 100% 3D printed respirator for COVID patients, which will allow you to basically build at home your own respirator in case you need it. But before I start with the work, as I said, I would like to take the opportunity to introduce to you the Center for Innovation and Creativity that was founded by the Technological University of Querétaro and the National Autonomous University of Mexico in 2016. This is the very first center of this type in Latin America. It has had a very strong impact, not only in Mexico, but also in some other Latin American countries. We are now discussing the possibility of replicating this in Argentina, Peru, Colombia, and Puerto Rico, and also Chile. And last year, some authorities from University of Illinois, Urbana-Champaign, including, of course, Professor De Mejia, had the opportunity to visit this facility in Querétaro, and they can tell you firsthand what they think. First of all, let me tell you why Querétaro. Querétaro is one of the smallest states in terms of size in Mexico, but this ranked among the top in terms of research and technology in Mexico. We have 52 research centers in a 1 million inhabitants city, and over 110 universities in the metropolitan area. We have one of the largest economical growths in Latin America, 7.7%. And we have many hubs. For example, in the automobile industry, we have over 350 companies. In the aerospace, Querétaro is one of the most important hubs in Latin America. We have over 80 companies. We build a small place here, 100%, in information technologies, in biotechnology, in medical technology, and plastics. We have many industries. So the concentrations of talent in Querétaro is very high. Querétaro is ranked among the top 100 most innovative cities in the world. Is tied with Toulouse in France. And we have this center which gathers not only research from the Technology University of Querétaro and UNAM, but as you can see here, some of the leading companies in this Industry 4.0 technology: Intel, Siemens, Cisco, Bros, Microsoft, Fortinet. So it's a very interesting area, because in the building, which is very beautiful, the state of the art in terms of technology and facilities, the people next door to you is a person who belongs to some of these different leading companies. The complex is formed by two buildings that you can see at the bottom picture in the aerial photograph. And one of the ideas that we discussed last year is the opportunity to have an office, a facility from University of Illinois system here to take advantage of all the talent and all of this very high concentration of technology in Mexico, which is a gate to Latin America. And also for us, will be very interesting to have direct contact through our colleagues living or staying here in Querétaro, Mexico, and with the Illinois system, which is one of the most important university systems in the United States. Now let me tell you about the specific problem that we are going to present in this opportunity. We live in a planet that has a lot of water. And the idea here is that that 70% of the crust of the planet, which is covered with water, is basically wasted because it is salty and has very little use for energy conditions. So the idea here was to construct a low-cost hydrogen system to extract hydrogen, which will be used for many applications, as you know, from basically rainwater, drinking water, and wastewater, which has been cleaned by some of the technologies that we have seen here. The idea is that since this Center for Innovation and Creativity 4.0 has very good capabilities in state-of-the-art information technologies, Internet of Things, embedded microelectronics, the idea is to produce a system which is fully automated and could be controlled through your mobile phone to produce water in a very simple way. This is the simple idea. You have the deposit of water, and through pumps and different controls, you can replenish the container or obtain water from the container. This water is obtained from recycled water or from even from the air or from salty water, and by obtaining through electrochemistry system included in the design that you can see on the upper hand right hand side, we can obtain the hydrogen to charge batteries at different levels, and while controlling the voltage level, the cycling, and the current that is being produced. The advantage here is that everything is fully controlled. It has state-of-the-art electronics. This is part of the design, some of the equations that control the flow, and the system has artificial intelligence to control not only the flow and the different parameters, but also it has attached a system that can control the meteorological conditions like humidity outside, humidity inside, to be able to make the most efficiently possible the collection of water and the taking advantage of the water there. This is some of the system that shows you how the software, which is embedded, meaning that we have the possibility of producing our own chips, microcontrollers, and in the microcontrollers that are built in-house, we have the software that controls all the systems parameters, including external humidity, amount of water, quality of water, and everything. And I'm mentioning this because some of the work that we have seen today, in particular, Professor Germán Buitrons, could take advantage of this fully automated system for the things they are doing. We also have a system to predict the weather conditions from frosting conditions due to changes of temperature and humidity inside and outside, and being able to control this basically. So as a conclusion, we would like to offer this system is working at the laboratory level, at the prototype level, and we would like to share some of the results with interested parties to see if we either can apply all the capabilities of artificial intelligence, Internet of Things, and embedded microelectronics to some other applications, or see how we can expand and scale up this system to really be able. As for today, we have about 50 square meters laboratory, which is completely fed by this system in terms of energy and in terms of water. Thank you very much.
Okay, thank you very much, Victor. Great. I think I missed, so questions? Please post them. Victor, one general question before we move on. So have you calculated, I missed that, the cost of electricity, the LCOE?
Yes, it's about 30% cheaper than the cost of great energy that we use for the laboratories. But we believe that this could be improved by basically scaling up the size.
Okay, perfect. Yes, yes. It looks, and also it's scalable, and then off-grid, so
yes,
has many advantages. Okay.
Exactly. Thank you.
Okay. Thank you, Victor. Okay, so our last speaker from this first track on renewable energy is Andrew Stumpf, a principal research scientist, geologist, affiliated to the Institute for Sustainability, Energy and Environment, IEC. Okay, Andrew.
All right, just a minute here. How's that?
Good.
Okay.
Thank you.
Thank you for inviting me this morning. Just wanted to, next 10 minutes or so, give you an overview of some of the geothermal research that myself and others on the University of Illinois Urbana-Champaign campus are doing. Here. So basically the background is geothermal systems. They use water wells and pumps, piping and pumps to basically bring the ambient thermal energy in the ground up to the buildings and circulate it through the building heat and cooling systems. Because you're using ambient heat in the ground, it significantly reduces the amount of other energy you need for for heating and cooling buildings, which will be important aspect of decarbonization of heating and cooling systems in buildings. So at the Illinois campus here, we've co-founded the Illinois Geothermal Coalition, which is a group of staff, researchers, students, and faculty, which are trying to support the advancement of geothermal energy in Illinois and the U.S. Midwest region. And as you can see, we have a number of departments involved on campus, a number of companies, a number of nonprofits, and industry professionals that are involved in this coalition. And we're trying to collaborate and connect the engineering world, science, the geology and hydrogeology worlds to make these systems more efficient and provide energy in different buildings and other facilities. So when we talk about geothermal energy, typically you would think probably about volcanoes and steam and hot water, but here in Illinois, we don't have those resources. So we are using resources that are shallow in the ground and are relatively low temperature, so below 150 degrees C, to do heating and cooling, either using heat pumps or doing direct use, where we're bringing the heated water to the surface. And we call this geo-exchange rather than geothermal because we're exchanging heat from the ground into pipes that we circulate water through. So we're actually using the water as the medium to do the exchange of the thermal energy. And here on the right-hand side of the slide here, we can see example actually from Mexico, from Pueblo State, where you have a horizontal trench where you have the black pipes that circulate the water in the trench, and then beside that you have in the building you can either circulate the heated water through the floors, or you can run it through the HVAC system, the air system. So it's either a water-to-water system or a water-to-air system. And then there's an example here of a heat pump that's attached to a hot water heater. So you can actually make hot water as well when you run a geothermal heat pump. So the Earth acts as a thermal battery, absorbs around 40 to 50% of the solar energy that's coming from the sun. And so it's heating the ground throughout the year. You can actually see within the top, say 15 meters of the ground, you can see the seasonal changes in temperature over time. And that's the graph here on the bottom right, where you see the temperature changes as you go down from the surface down throughout the year. But as you get down below 15 meters, say 40 feet, that's where the temperature becomes constant. So at that depth and below for a certain amount depth, the temperature remains constant throughout the year. So that actually is the perfect depth to have a geothermal system, because you know you have a known thermal energy resource throughout the year. It doesn't change, and that allows the heat pump to run more efficiently. And also the actual climate in the region is actually relatively important in these systems, because you actually want extremes in climate. So for example, in Illinois, we have cold winters and hot summers. So you're always trying to change the temperature in the buildings to your 22 degrees Celsius or your 72 degrees Fahrenheit. You're always trying to get to that temperature. So if you can bring water up through your geothermal pipes that are between, say, 51 and 56 degrees throughout the year, then your change in temperature within the building that you're trying to get to is much reduced. So that allows you to use less energy to actually fill that gap in the temperature range. And the temperature in the ground is really, it's dictated by the geology and the hydrogeology. So depending on what your geology is, it can be a more efficient thermal sink, or it could be a better source of thermal energy above ground. So here's another diagram where we're just showing that in the summer, you're trying to bring your temperature inside to around 70 Fahrenheit. So you're trying to, you're rejecting heat from the building into the ground. And you might be able to store a lot of this throughout the year during the summer. So that can then be pulled out in the winter. So then you're trying to get your indoor temperatures when it's cold outside. So you're not directly being impacted by the seasonal changes outside. You're trying to tap this constant 55 degrees Fahrenheit temperature in the ground. And here's I wanted to just show that when you're looking at energy demands in buildings, a lot of different energy sources, you have a peak throughout the day or throughout the years. And so it fluctuates a lot throughout the seasons of throughout the day, where the geothermal energy has your constant load that you're providing, and you're using a relatively narrow amount of energy to pump water through these pipes. So it really flattens the peaks in the energy usage in the buildings, which is very important because that reduces the cost overall. And the cost of running geothermal systems are much lower than other sources of energy, as we can see in this diagram. And also, geothermal energy provides really you're using one unit of energy to do the pumping. The ground is giving you 3 units of energy from using this one unit of energy. So you're actually gaining you're using 4 units of energy, even though you only use 1 to actually run the system. You're gaining these extra 3 units. So that's very efficient. These systems run throughout the day, 24 hours a day, 365 days a year. So they're always running, always available. They're not impacted because they're below ground. They're not impacted by any storm events or any outages at the surface, because you're using a small amount of electricity. You're reducing the amount of carbon being generated by heating and cooling. And again, because it's underground, you're using very little space. So you can put it under parking lots, you can put it under buildings and soccer fields, whatever. You're not using much surface space to install these systems. In Illinois, or in the US, the Department of Energy came out with a long-term vision for geothermal energy. And so they identified Illinois as a place where significant expansion could occur using ground geothermal heat pumps. So we're trying to promote the advancement in Illinois and the Midwest. Also in Mexico, there's a large source of shallow thermal energy that could be used, and the group Geo is promoting research there to use geothermal heat pumps for heating and cooling. And if you look at the thermal energy uses of all different users, you can see that many of the uses of thermal energy are in the low temperature area. And so what we're looking at here, we're actually covering about 7 of the 11 applications in Illinois just using the low temperature resources we have. We can either do that with the heat pumps or direct use for deeper bedrock units, directly using the heated water to the surface and not using a heat pump necessarily. So geothermal systems with heat pumps, they can be a number of different configurations. They can be vertical boreholes connected to a piping system and then connected to the heating and cooling system in the building. You could use, like I showed before, you can use horizontal trenches with the pipes. You could also install a heat exchanger in a lake or a pond or a river to get thermal energy that's stored at the bottom of these water bodies. Or you could use water wells to pull the water directly into the building and exchange the heat off the water and then return it back to the aquifer. And some of the new technology, they're actually installing the heat exchangers in the actual well, so you don't actually have to bring the water to the surface. You just run the water through the heat exchanger, captures the thermal energy in the well and pulls it out into the building. And I think long-term, if you could do this, you could actually turn a water well into also a geothermal well and actually get your water and get your thermal energy from the same well. In buildings, you can actually install geothermal loops in the structural supports, the piles that are in the building structure, the foundational parts of the building. And because these you're already drilling these for the structural components, it's basically it's free. So you install your loop inside of the cement piles, and the drilling part of it's free, which usually is about 50% of the cost of building geothermal systems. So if you can save money installing them, then that's another benefit. And the focus of some of the new research is actually connecting these geothermal wells in tandem in a circuit between buildings, so you can share thermal resources between buildings. Some different types of buildings have different types of energy loads, so you can actually share the thermal energy, whether it's cooling or heating, between the buildings. And this is much more efficient, and you share the actual construction cost between a number of users rather than a single home or a single building. And these can be very beneficial systems in cities where you have a number of different energy uses and buildings have different energy loads. And you can see here one of the projects we're working on, we're looking at cities as a place we can develop geothermal systems. Because you have a lot of waste heat that come from buildings, you can actually store that underground in different geologic formations to reuse later. And so you're not releasing this waste energy, you're not using it. You can actually store it underground over time. And also developing these geothermal systems, you're creating a whole new workforce to install these systems. So you're actually creating jobs and creating economic development with the advancement of geothermal systems. And we on campus here, we were involved in several projects. And this project here for the campus instructional facility, just bringing the research into the design of the systems, we were able to reduce the actual overall cost of this building, this geothermal system for this building, which was pretty significant. So that's it for me. Thank you.
Okay, thank you very much for the presentation. Very, very, very interesting, Andrew. Okay, I think we are on time. This concludes the presentation for everyone. This track one. Thank you all for presenting this very relevant research, interconnected research, tackling fundamental and very pressing problems in our society.